All right, so welcome everyone. We're excited to have you join us for our February session of the Transportation STEM webinar series. And today we are very excited to have Dr. Mina Sartipi joining us. She's the founding director for the Center for Urban Informatics and Progress at the University of Tennessee at Chattanooga. And she's also a professor in the Computer Science and Engineering Department. She has research that is funded by the National Science Foundation, the National Institutes of Health, Department of Energy, State of Tennessee, and a variety of other organizations that focuses on data-driven approaches to tackle real-world challenges in smart city applications. So I think this is going to be a really exciting session for all of our students and teachers that are joining us. Again, we're really glad that you are here today. So welcome from the National Network for the Transportation Workforce. And we are going to go ahead and get started. And I'm going to turn things over now to Dr. Sartipi. And I will just also remind everybody that as you think of questions, you can go ahead and type them into the chat, and she is going to answer those at the end of her presentation. So welcome, Dr. Sartipi.
Thank you so much, Dr. Ivy. And I'm so glad and excited to be here to talk a little bit about some of the work that we are doing at UTC, University of Tennessee at Chattanooga, and also City of Chattanooga. I'll be talking, this is a very broad topic of data, traffic management, and also resilient cities. Basically, what we do mostly is related to smart city. And we do get this question that, what do we mean when we talk about smart city? This is a very, again, a big picture, and I'm going to be focusing on a couple of projects that I will be talking about. When we talk about smart cities, part of it is about, okay, so where can we get data? Either the data already exists. We're going to talk about projects that, like for example, data is from 911. It's public, it's open, every city, every person can have access to. A lot of these data has been collected and has been stored for a long period of time. What can we do with this data to make our cities safer, to make our cities more resilient? And this is the goal for us. And within that big umbrella, huge umbrella that we're covering is what are the areas, these are some of the areas that we are focusing on. When we started the CUIP, Center for Urban Informatics and Progress, one of our goals was to not to do the research just for the sake of research. We wanted to make sure that we were working on meaningful and impactful projects. That's why you see the social science on top left there, that we wanted to make sure that the problems that we are planning to work on or we are working on really is something that our community, larger community, the state, the country, the world is seeing it as a challenge. And if we see that as a challenge, how can a data-driven approach solve that? And the next question we always ask is, can that be implemented? Because we don't want a lot of things to stay in our lab and just be good papers, funding and such, the students graduate, but would it be able to be implemented and we see the impact of it? So that is a core belief and vision for our center. Within that, we work on different problems. We work on energy, water, wastewater, traffic, health, and a lot of related projects to this. But today, I'm mostly going to be talking about transportation projects. And that's one of the areas that we are more focused on because of the close collaborations that we have with the City of Chattanooga, Chattanooga Department of Transportation, and specifically Kevin Comstock, who is the Smart City Director for City of Chattanooga. And when we talk about any of these projects, it's always good to see that, okay, what are we trying to do? What is our goal? Because it's when you start doing research, you can very easily get trapped into the weeds and just forget about what was the goal. So when we are talking about these projects, we do have some metrics. These are all defined by either the community had told us that they feel, for example, related to traffic fatalities or related to the public safety, or the city has some plans for it. These are some of the metrics that we are working on. Vision Zero is when you are eliminating all traffic fatalities or severe injuries. Or in terms of fuel consumptions, in terms of emissions, what are the things that we can do related to that, and making sure that, like, for example, how can we improve emergency response time and such. So these are the metrics that we have defined, and I'm going to be talking about some of it that are related to these projects that I will be talking about more. One of the things that came up very early on in our conversation, and this is maybe 5 years ago, 6 years ago, was we all seeing it more and more distracted drivers, distracted pedestrian? How many of us are crossing the street and we're just looking at our phone on crossing? And unfortunately, that's happening also with the drivers. And we are also at the same time, so that is obviously causing accidents, causing not safe streets. But one of the things that we are seeing more in terms of transportations is connected and autonomous vehicle. You know, we are not there yet for fully automated vehicles. It's going to take some time to get there, but there is the first part of it that is the connected. And what do we mean by connected vehicles? If we allow the vehicles talk to each other, if we allow the infrastructure and vehicles talk to each other, what does that mean? You're driving down the street and the traffic controllers, there was a camera there, it had seen there is an object on the road, or it sees you're driving and the car sees a black ice. The cars that are coming after you do not have to go through the same experience that you have gone through, because that can be broadcasted to other cars. We can communicate the situation with them and let them know about that, so they can make a decision faster ahead of time, to be more proactive versus being reactive. And that is where we are quite a bit focusing, we are doing our focus on the connected part, that what are the things that we can learn from what vehicle had seen, what the infrastructure had seen, and share it with each other. And we probably have seen this slide about the different level of automation in the vehicles and such. So we're more talking about the cases that, what are the things that maybe a level 2 car can do, potentially some of the things that the level 3 can do, but we're not getting to fully automated. And I brought few slides that talks about, because I always think that it's also important to show the progress of work. When we started working in the connected vehicle, one of the questions we earlier on got was, and this is back in 2000, early, like maybe 2012 or so, that we were working on looking at some of these. And the question was, we are counting a lot on the GPS. What if GPS is down? And what are the things we can do to make the roads still safer, to make sure that in case of the automated vehicles, in case of like limited levels of the automated, how can we make sure that the vehicle would get to the destination safe? So we built this test bed on campus because we wanted to understand what is going around a vehicle. How can we get the holistic view of our environment? This is a case of the data doesn't exist. So we knew that, okay, we have to build the test bed to be able to get access to that data. So we built this on campus. It was a very simple, we put connectivity, wireless connectivity on 3 of the poles. We put 1 camera there, and they all connected to the fiber. Through the fiber, we send the data back to our data center, process, and send it back. One of the very early on projects that we did on this was, and this was our research group. And the reason I brought this, because I'm going to also show you where are we now. We didn't have capability of we didn't have any partnership with the city. So we actually held the camera. Jose that you see in this picture, he was my master's student. He's very tall. You can't see me, but I'm also very tall. So he and I were the ones that we were holding these cameras and at times that we needed rest. So it's just it was like that level of, things that we had to go through to collect data. And the fact that it was not installed on fixed poles, we also had QR codes. So we used these QR codes as reference points. So our camera would scan it, so we would know where things are and how can we find the location of each vehicle and such. And these are all the students and postdocs that are behind the work that we did about 8 or so years ago. And this is actually, these pictures are the case that we had high school students and teachers came and visit us and learn about these projects. And one of the very first projects that we work on this, we called it see-through, was what if you can see through the car in front of you? So this is, so what you see here is the view that the car, this silver SUV is getting. This person was crossing in front of it, and the car in front, the black sedan, was sending that information back. So it overlays with the view of the car, with what the car sees itself. So this is the case that if we were able to let the car in front of us had seen something, or the infrastructure had seen something, overlay that information with what you as a driver can see or the car can see. And this is the case of basically machine learning, deep learning, computer vision, whatever we want, image processing, that You get that information and overlay it with what you are seeing and then make the decision. In this case, the red SUV is turning. You don't know what is coming ahead of you. So by sharing the data from the car in front of it, then now it can understand what's going on. So it would know about the safety of the pedestrian. So for example, if a pedestrian is crossing in the non-designated area, how would you be able to understand it? And then like you see the car in front of you slowing down. So you're like, I'm going to pass it, but maybe he slowed down because a pedestrian was crossing. And that way you would get that information. So this is kind of like the concept behind it, that each vehicle send the data back to a server. It can be an edge computer. It can be a computing basically close to the street on the pole somewhere. It can send it to a data center. It can send it to the cloud and process it, and it comes to the overlay and it comes back sent to this vehicle. So it can use that information. So these were the type of topics that we were working on. And we did quite a bit of studies that what would be the reaction time of the driver, for example. And where the STEM comes in for projects like this is, I think in this case is kind of obvious. You have a lot of data that we are collecting because you're driving down the road and you're collecting all these videos, you're processing it, and how would you be able to do this in a way that you can identify the object? There is a pedestrian, you need to slow down. I have seen a cyclist down the road, so be on a lookout when you're passing by that person, and all of us, and send them back in a real time. So that then we realized that, well, that's all great and everything, but there's a limitation because this was a small street on campus. We didn't have any, for example, traffic lights or much of it. We had a lot of students walking and such, but we didn't have much traffic there. That is where we moved to building another test bed in downtown Chattanooga that we call it MLK Smart Corridor. It's along MLK Boulevard. It's 1.25 miles of the road. And actually 2 days ago, this became 11 signalized intersection. We added one to the Pine Street, but basically we have different intersections that we added different IoT devices. And we chose this street is because it's in downtown. The campus is on this side. So we do see a lot of walking still. And there are some businesses closer to the downtown. And as we move toward the east, we see more residential there. So it kind of like represents the campus. It has a car charging station. It has a bike share station, and it has bike lane and such. So it kind of represents all of the things that we were interested in looking. And so this is one intersection, and these are actual pictures from that you can see that we have cameras, we have audio sensor, air quality, LiDARs, some of them. And then we put a lot of different wireless communication. Those of you from transportation, by the way, I'm not a transportation person, I'm learning every day. But one of the things is we want to make sure that as the Department of Transportation changes their standards, we are still going to be able to use the test bed for that. So we have a lot of different wireless connectivity there. And I did mention edge computing because some of these applications, it's going to generate some of these devices generate a lot of data. So it's going to be expensive to send them back, and also the time sensitivity of it. So we do have some of these computers in these basically in these cabinets that we process the data right there at the intersection. And one of the things that I'm going to just say at the beginning, we did before we set this up as part of our social science research was we didn't want anybody to leave their house or business and come back the next day and see their cameras. In fact, some of our intersections has 3 or 4 cameras. We knew everybody, we care about privacy. I lived in this city, I passed by this, my office is in front of it. So we all care about that. And one of the things is we do not store any videos or any audio. We process everything in real time and we drop the video. And I'm going to show you what kind of data we collect. And in terms of audio, the only things that we listen to is gunshot, and those are the frequencies. We look at the gunshot and siren because we want to see that if an emergency vehicle comes, how can we adjust the traffic controllers? And so what I showed you was this part of the MLK, and I'm going to talk about a couple of projects that we are working on MLK in terms of the urban mobility, in terms of improving the safety, making sure that the streets are accessible for everybody and such. But we also understand that urban streets are not the only streets that, like, the need for the urban streets is very different than the need for the highway. As we move toward more automation, we also are expanding our testbed to the highway, because that gives us a different sets of data that we can work on. For example, lane changing, car following. So there are things like that that we are also interested in to see for the highway. So this would be the general case of, believe it or not, we see so many wrong way detection vehicles going. So in terms of, there is a ramp here that you're exiting, but we see cars going the wrong direction. There's another intersection I'm going to show you that we see the cars go to the different direction. And the things about these type of projects that we collect data to understand it, we have data to show our case, where it says, oh, Mina has seen 2 times that a car goes in the wrong direction. So it's not like that. We actually have it with the proof of these are the cases that it's happening. So now the next step would be, what can we do to mitigate these cases? And that is why it's so important to be collecting the data and analyzing it to see what is going on and what are the things that we see that it's causing potential accidents or high risk for pedestrians. Very first thing that we did with this data, what you see here on the left is, as I mentioned, we see the data on the cameras. This is one of our intersections. Actually, my office is right here on the 2nd floor. And one of the things that we did was we see the objects, detect them, and classify them. So we are saying that this is a car, this is a bus, this is a pedestrian, this is a truck. And based on that, and so that is the only type of data we collect. And then based on that, we can make a heat map. We recognize there were several parts on this street that we saw people crossing in a non-designated area. It kind of makes sense after looking at it, because this is the starting of campus and there's a lot of free parking in this site. So we can see that, during the day, there's a lot of students, staff, faculty park here and then walk to campus. And you can see that, we see the pink is showing pedestrian. We see obviously the pedestrian on the sidewalks. We see pedestrian here, which makes sense because we have eliminated, we have basically removed the vehicles out of here. People park here and get off their car to move. So we can see these are all make sense, but this doesn't make sense. These are the areas that we need to be alert about to see what can we do there. The other thing that we saw was the buses and trucks, because this is a bike lane, they also go to the bike lane. So how safe is it, our bike lanes? And these are the things that we want to be looking at. And up to this point, this is purely visualization or descriptive analysis. We're not applying any optimization, any learning, any training, nothing there. At this point, all we're doing is, okay, so I have identified these objects and I'm just drawing a heat map of it to see what's going on around this area. And so, well, to get to that, the very first thing we talked about was the object detection, right? So you want to be able, I'm not going to go through the algorithm behind it, but there's a lot of details in terms of computer vision and machine learning, deep learning that we are working on to get there. But basically the goal is when you see these objects, how are you going to be able to classify them? Because the important thing is, if you think about the camera and the camera view, when an object gets to the view of the camera, it probably looks like this. And by the time it leaves, it looks like this truck here. So we want to make sure that from the first time that the object got to the view of the camera, by the time it left the view of the camera, it's seen as the same object. Because one of the things we're interested in is traffic flow. We want to know that how many cars are passing by, what is the speed, what is the travel time, and all of those things. So it's important for us to be able to detect the objects and uniquely identify them. So that is the first part of the project that we work on. So basically, we do multi-object tracking on a single camera to make sure that these are all the objects that are the same object is being identified the same way. And you can see some of the results here. For example, we do different levels of classifications for different projects that we have. For example, we have a project that we are looking at fuel consumptions. When you're talking about fuel consumptions, SUV and a truck and a sedan, they have different fuel consumptions. And remember, we are not counting on knowing everything about the cars. We're not assuming the cars are connected, that they can send it to us, because that's not the reality, and that's not going to be the reality for a while. We're going to have a lot of mixed traffic cases for a while. So in this case, we are training our algorithms to be able to detect this is a truck, this is SUV, this is a sedan, and we see them in a different categories in terms of fuel consumptions, in terms of emissions and such. And one of the questions we get often is about the EVs. We have another algorithm that actually can detect to some level of accuracy. I'm not saying it's 100%, the model and the year of the vehicle as well. So some of the vehicles we will be able to do that. If it's a hybrid vehicle, it's hard. It's actually impossible to see that. If there are cars that they are plug-in, but they also have it without the hybrid version, it's hard to see that. So there's a limitation to that. So this is one part of the work that we are working on. The other, that is the third block down here, as I mentioned, because of the privacy issues, we're not looking at any license plate. So now I see the car coming. It was passed through this intersection. We gave it the ID of 1, let's just say. And it passed through the next intersection. Is this a way for me to detect this was the same object? So I give it the same ID. And that is when it becomes multi-object, multi-camera tracking. Can we detect the object from the beginning and being able to track it as it passes through the intersection? One of the main things for us there is travel time. One of the things is the speed, because we don't have a view of every intersection. There are mid intersections that there's no camera is covering it. So we won't have the view of the whole complete view. So we want to be able to work on this. This is an ongoing research that we are doing. We have some results that I'm going to show here, but basically this is what we see. So the vehicles are moving from west to east. This queue of vehicle passed by one of our intersection, Lindsay, and then they passed some of it turned, some of it didn't, and they passed through Houston, which was the next intersection. So we were able to detect that. And again, we are not using any identifiable information, so we don't have their license plate, but there are some features that would be part of the computer vision algorithms that we are using, optimization and learning process, that there are some features that we can learn from these, that we can apply it when we see the object again, that what was that object. I'm going to show briefly this. This is, before starting this, I mentioned that we did quite a bit of focus groups and such. And one of the things that came about was people feeling like they didn't have enough time to cross the streets. They didn't feel safe about it, because it's not necessarily just not the time, but also the ones that are turning left, that they feel like it was just too close. And these are the cases that we call it near miss. I've heard the different terms for it, but basically it's a case that accident or the crash didn't happen, but it was close to happen. So these are the high risk areas that we are talking about. And to find that, one of the very earlier on projects that we work on was, okay, so we built this model that you can see that all the objects are getting identified, detected, and I have a label. You see that we have a track of where object came from, and we are predicting where is it going to be in the next second or so. So if we know that where's the car going to be in the next second or so, where's the pedestrian going to be, and if they're getting too close, it would be a time to collision, that it should be an alert. And that is what we just saw in the case there, that there was a minivan got too close to the pedestrian, and then we had like calculating the time to collision. So while this worked, and we worked on it for probably more than a year, and we realized the limitation. And I think that's one of the things that when you're working on projects like this, that it's when you deploy it in a real world, you will see the limitations. And because of the limitations with camera, because it's 2D and there's no depth to it, it's hard to find accurately the distance between two objects. So that was one of the things that happened in this case. And through that, we were like, okay, so there's a limitation. What other sensor we can use? And that was the time that we had, let me pause these both of them for a second. This is when we started using LiDARs. So this is, we are working with two industry partners, that what you see in this case is, this is a little bit ahead of this. So this is the car that it's going, turning left, and this is the car that it's going straight. The vehicles or the are being boxed with red, and the pedestrian are being boxed by green path. And what I want you, I'm going to run it a little bit so you see them in parallel, and you see the other good thing about this, there's no privacy issues here. But what I want to show you is here. Let me pause this for a second and get them both to the sync. So you see that this person is about to cross. And so we do these data collection in addition to what we collect 24/7 from the test bed. We also collect data from ourselves, like we go out there and collect. I want you to pay attention to this person crossing. Okay, and now look at it here. So this person is about to cross. It was the same person that was going, and look at this. This is a case that if he had not moved, this would have been an accident. So this is the near miss. This is something that we need to be alert about and understand that these are the left turns that are happening, that more than once we have seen that it's not, the people that are crossing are not safe about it. So, again, these are the cases that we are collecting the data, we are analyzing the data and understanding what's going on. And then the next one I want to talk about is in the same intersection. One of the things that we when we talked with others was, are we really making all our streets accessible for everyone? You know, we talked with a lot of community partners, and there are problems that, you know, on a day-to-day basis we see it. And I'm not saying we are ignorant, but probably not paying enough attention. One of the things was, are we giving people enough time to cross? So this is a case of a person with disability that is crossing the street. Do they have enough time to cross? Or a parent is pushing the stroller crossing, or an elderly taking longer time. What are the things we can do to make sure that everyone feels safe when they are crossing? And in this case, what we are doing is, because through the partnership we have with the city of Chattanooga, we actually have access to all traffic controllers, not changing it, but getting the data from them. So we know exactly at each intersection, what is the time, what is the situation now, how much time is to green, how much of it is left green time, left red time, and such. So we have all that information. And one thing that we did with this was we actually had a data challenge on this, that when you observe that you understand that the system is seeing a person that is crossing needs extra time, how can we adjust the traffic controllers to accommodate that need in real time? But it's also important that, you know, it's not as simple as, okay, just increase it by 5 seconds, but just by increasing one intersection by 5 seconds, we also need to understand what is happening in the city, all the intersections around it, because we need to be doing this in the collaboration with all other intersections, at least the ones around it, to make sure that we're not causing traffic somewhere else, or we are not making another area not safe. So these are the things that also we need to be thinking about. And we can see that it's really a simple case of looking at the data that comes from either LiDAR or camera, analyze it, understand the trajectory, understand where's the object going, how long is it taking. And then also we get the data that comes from the traffic controller. So what is the pedestrian light, how much time they have and such, and being able to coordinate, like correlate these things and understand that, okay, so we need to increase it or not, or it's good and such. And so that's one of the projects that we have been working on. The other project that I'm going to be talking a little bit about is crash prediction model. You know, the project that I just talked about was a case that we saw the data was not there. So we came with the partnership with the city, with our power company, EPP, and other partners in the community. We were able to build this test bed, and we are learning from that. And we are trying to see that, okay, what I have learned on this corridor, how can I apply it to other part of the city and eventually to other places? This project that I'm about to talk about is in terms of crash prediction. You know, this is the one that I mentioned at the beginning of the talk, that we were approached by our 911 response, the emergency response, that they have been collecting data since 2017. That the good data. I mean, the data has been collected for a long period of time, but this data is it's in a good shape. It's fairly clean and everything. So the question was like, what can we do with this data? Because we have seen the traffic deaths in Tennessee is growing. In case of Hamilton County, we have also seen the number is growing. The severity of accidents are growing. So the question was, how can to remedy this issue? What can be done? Like any project, when we have data, the first thing we do is visualization. So in this case, we are basically what this graph is showing you is the accidents that happen in our county, Hamilton County in Tennessee, in terms of the hour of the day for different days. And you see there is a trend there. You see that as there are the morning peak hour and afternoon peak hour of the weekdays, we see more number of accidents. Overall, in the weekend, the number of accidents is lower. The other thing that you see is, the number of accidents is peak at 5 p.m. on every day, but on Friday is 4 p.m. Probably people going home earlier that day. So these are the things that we see that there is a trend. Whenever there is a trend, we can learn from that and we can see that, okay, can I use this to predict tomorrow afternoon or like a Tuesday afternoon when it's going to be raining in Chattanooga? Can I predict where are the areas that are going to have high chance or high risk of accidents? And the other thing we did was, so the other one shows us the correlation in terms of time. And this one is showing us the correlation in terms of space. So it's spatial correlation. You can see that. So this is our county. And there are two main highways passing through. This is Highway 75, which 24 goes to Nashville area, and the 75 goes to Atlanta or Knoxville. And you see that in the morning, more accidents are happening in this part of the city. And as the day progresses, the more accidents goes toward the 75. So again, we see that there is some level of correlation there as well. So what we did, again, this is a case of purely descriptive analysis. So what we did here was we zoomed in one area and we saw that this is a residential area with a speed limit of 25, but there were over 70 accidents in this hexagon. That's an anomaly. That's like a lot of number of accidents. So we saw this, we reached out to the city and we to ask them that, okay, so what do you see as a problem? And they told us this pole was too close to the street. This is an older part of the city, the sidewalks are narrower and everything. So there wasn't much we could do there, but they moved it by probably a foot, and they also add a reflecting sign on it. There has been no accident since 2019, June of 2019 on this road. And this is the type of impact we would like to see. And again, this is purely looking at the data, saying that, well, there is something going on here. There are no many accidents. What can we do? But we wanted to take it to the next step. And the next step was basically, is there something we can do to be able to predict it? So can we say, where do accidents occur? And the next step after that would be obviously, what can we do to mitigate those things? So I'm not going to go through too much details here, but basically we have collected data from 911. ETRMS is basically, we get it from Tennessee Department of Transportation, tells us how many lanes the road has, what type of curvature, does it have shoulder, where are the sidewalks, and that type of information. We use GIS and also weather, local weather, because that's the important thing about the visibility, about roads being wet, about ice. We don't get much of snow or ice here, but like all of those things. And using all that data, like every data analytics project, you do a lot of processing, cleaning, aggregation and such, and then we built our model. What we see here is one example that we looked at it. We looked at the data from the beginning that we had from 2017 up to January 22nd. And what you see there in terms of the hexagons are where we predicted the accidents may occur on 23rd. And then on 23rd in the morning, when we received all the accidents for 22nd, then we plugged them in. And you see that there were a lot of areas that we were able to predict where the accidents are going to be happening. So one thing that I want to mention here is that we are learning based on this is we are building actually dashboards and such for this, that the emergency responders can look into this and can see that, okay, so it seems like this is the area that has higher risk of accidents. How can we reallocate the resources? And understanding where are the fire trucks, where are the ambulances, where are the hospitals, and all of those to understand better, because every budget is always limited, resources are always limited. How can we optimize that with the goal of reducing the response time? Because we all know that the first few minutes of the accident, responding the fastest is the most important in terms of the long-term results for those that have been in severe accidents. And what we are trying to do, what I'm showing you here is, you might have heard the term digital twin. Because, I talked about two projects here. I talked about the testbed, several projects that's going on the testbed, and then I talked about the accident. So a lot of things that we can learn from these is, we might come back and say that, okay, change this traffic light, or add a sidewalk, add a stop sign there, or any of those things that we can come up with. How are we going to be testing it? The problems like this, that is a real problem, real challenge. We can't just go out there and just say, my algorithm said that this is a good optimization result, let's just deploy it and see. Obviously, that's not an answer. So what we are trying to do here is, we are building all that scenario in a digital sense. So we are building it in a simulation environment, which is called digital twin. So what you see here, and I'm going to bring it from beginning so I can show it to you. So this is basically the test bed. So we are building this digital twin. So all these vehicles you see, this is obviously, I took a screenshot because I wasn't sure the process. It takes quite a bit of processing. But the goal is, when I look out the window of my office, which is test bed is right there, it should show me the exact same thing as I'm seeing here, in terms of how many cars are there, what is the queue length, how long people are waiting to cross, and all of that. And in terms of that, so this would be a real replicate of what's happening in the real world. And then in this simulation environment, I can come and run different scenarios. I've seen people cross jaywalking, so let's just add a sidewalk there with these scenarios. How is that going to be impacting the traffic? So there's a lot of type of works like that we are working on in the simulation. So this is the exact replica of the test bed. And you can see that we can follow the vehicles passing through and such. And I want to mention that there are a lot of students involved in this work. Obviously, the students are the force behind all the work that I just presented. And areas like this smart city project are truly multidisciplinary. We work with undergraduate, master's, PhD students coming from all different backgrounds. Depending on the work that we are doing, they come from different backgrounds. And we also work with high school students as well. That we have a STEM high school here in Chattanooga that they use some of our data for their capstone project. We do some of these training related to some of these data. We go to some high schools as well. So there are really a team of students that are behind this and are making these things happen. So I'm going to, I think maybe I have a couple of minutes. I'm going to actually take you to downtown Chattanooga in real time, and I'm going to show you, let me re-share my screen. So this is the test bed that I talked about, and I'm going to show you some of maybe one or two of our intersections. So I leave enough time for Q&A. This is, let me show Central, probably has more traffic at this time. So what you see here, this is one of our intersections. These shows the number of volume of the traffic at each different direction. We see the air quality. This actually shows we're not doing a good job there. You see arrival by phase. So there's a lot of cars arriving at the red time. That means that this needs to be changed. The way that the traffic controller is working is not optimized. And this is actually a project we're currently working on. And then this is a real-time video there. So you can see that this is what was one of the intersections. So we see the vehicles, we identify them, we give them a label. And what you were seeing there in terms of arrival in green, arrival of red is how many cars got there. And then as they pass by, we look into like what was their time to cross it, how long did it take the queue be emptied, and such. The other one, I'm going to quickly also show you another one that's more in downtown area, that some of the other things that I showed you was from that. Again, these are showing, but we just try to, our dashboard, trying to show different parametrics in different intersections. Again, you see the approach volume here. We are looking at the PM 2.5, the humidity. These are like, we see that today we had seen 3 near missing cases. The other thing is like, one of our optimization algorithm, as I mentioned, was optimizing traffic controllers. We all have sat there. It's red, no other car in any direction is going, but we are just sitting there. So that is one of the things we're currently working on. But what also we want to make sure that we're not paying all of our attention to the cars. And what about the pedestrian? How long is it taking for a pedestrian to cross? Because that's also an important factor. So this is more in the downtown area. This is the intersection I was showing the person on a wheelchair and also the near miss happening. And I know I can't when it's in the sharing mode. But so I'm just gonna stop sharing and I'll be happy to answer any question.
Well, thank you so much. That was fantastic and so interesting to see all of both the systems you've developed, but then also the lab feeds that you're able to draw into your work as well. I have one real quick question to start us off with. Obviously, I'm sure computer science students are heavily engaged in your work, but could you share with us some of the other disciplines that students are coming from?
Yes. So we have students from all engineering backgrounds. We have mechanical, we have electrical, we have civil engineers involved. And what I was showing here was maybe very more heavily on the transportation part. So we do have electrical engineering, computer science, and civil engineers work together on these ones. The same thing with some, when we talk about digital twin and some of the simulation environment, we work very closely with mechanical engineer. Other projects that we work on in terms of EVs, for example, so we work with electrical engineers as well. And so it brings in many different disciplines. And in terms of other sciences, math, I think, is a clear reason that we would be working with a lot of mathematics students. We also work with different people from health applications because one of the things that, for example, we're looking to is air quality and asthma. And so part of it is definitely directly related to traffic. So we look into that as well as other factors and such. So we work with all colleges on campus, actually. And some of them come down to the business side and such. So we do work with the business and data analytics in the business as well.
That's awesome. Really great example, I think, of some strong interdisciplinary work. We have a question in the chat from Jacob Hall, and he asked, how could you realistically expand vehicle and pedestrian recognition data collection to a larger area like an entire city? And could infrastructure already in place be used?
That's actually a great question. So what we did, and I always say that this testbed, I call it the sandbox. I call it a sandbox that it basically, we added, I mentioned 4 cameras. Some of these intersections have 4 cameras. We have 3 LiDARs and such. But we started it. We didn't know what was needed. What was, there's a wish list, but what is really required to have. So we built this in sense of also understanding what is needed for us to be able to make our urban observable. And now we are actually looking into like more rural areas as well, or suburb, and they all have different needs. So what we learned from this is, and we are expanding it, we are expanding to a parallel street, but we are putting like 1 cameras now. Or we are tapping into the cameras that already exist in the city. And we will be able to look at some of the things that we have learned from here to other parts. The main goal for us to really make the urban observable, to understand what's going on, how the cars are moving around. But to your point, is it going to be trivial to go from one corridor to be able to say that this car entered, I don't know, like 4th Street and then, went through all these areas and then left at like Market Street? No, it's not. You're right. It's a challenging process and we don't have the coverage to cover all of those things. Having said that, we would be able to look into other factors like travel time and the queue length and all of those things. We would be able to scale it to a larger part.
Thank you. We have a question also from Jan Huffman, and she wants to know if you can talk a little more about how high school students are involved in your projects.
So this specifically, if the STEM high school, that the way they have been working with us was they come at the beginning of the fall semester, that because they do a two semester capstone project. So they come and meet with us. We tell them about our ongoing projects. We also tell them about the type of data that we have, that we can have it accessible to them. Obviously, we're not talking about the data that from beginning that needs to be clean and everything. We look into more the data that is ready to be used, because even at that point onward, it's still a lot of challenges that they have to deal with. And through those conversations, they come and meet with us, and we usually make a Slack channel so that they can have a direct, easier conversations with us, communication with us. And we define the project, or in fact, sometimes they define the project. One of my favorite one is from last year or 2 years ago, that the students came up with where are the constructions cones are. They design, actually, their team designed the sensor, a very low battery usage sensor, that it would just send a signal to some of the places that we had the receivers. So we would know that way we would know exactly where the construction zones were. And we were looking at different applications that, okay, you know that there's a construction, because believe it or not, a lot of times constructions happen without city knowing that the side of the street is being closed. So for routing purposes and such, and also where are the cones so they can later on collect them. So there were that was an example of they came up with their project, they designed the sensors and they collect some, or they come and just be doing a complementary work to what we are doing. For example, they developed the app for another case. But it's a very close collaborations that we do with these high school students.
Thank you. So I have another question. We have a lot of teachers on here today with their classes, and we have even more that were not able to join us at this particular time slot, but they're going to be sharing the video later. What would you say to a high school student or even a middle school student, that's really starting to think about career paths and opportunities, and they're getting excited about what it is that you're working on? How could they prepare now while they're in middle and high school? What are some of the things they could do to help them not only figure out what they might want to do once they graduate, but also how they can best position themselves to be ready for that?
One of the things that I believe in it personally, as well as the work that I'm doing, is we are going more and more toward the world with the data, a lot of data. So it's just this is because of the technology, because of capability of storing the data and processing the data and everything. So I think regardless of what anyone wants to do in future, getting yourself more familiar with some of these programming languages to understand, to be able to process, visualize. Again, not everyone needs to do predictive modeling, but being able to feel comfortable that a data was sent to you. How can I visualize it? These were just two projects. We have projects that we look at many different. The data comes from hospitals, for example, or the data comes from power company and such. The very first thing I think is just equip ourselves with the tools that we feel comfortable when a data is given to us, that we will be able to visualize it, to understand it, to just see what is it telling us. And I think one very, very important thing is, and this is definitely an area, and I think Dr. Arvi, you mentioned it as well, that multidisciplinary. It's just no one area would be able, if we only work with computer science students, we would not get anywhere, because we see data as just numbers. But the domain experts and being able to communicate these with others. So I think that in addition to the knowledge of what it needs from the STEM area, but also being able to communicate these with others that are not from our field. I always say that I feel like me being a computer scientist, it's just we speak Java, we speak C++, Python, that's our language. But that's not going to get me much far with this, because I need to talk to someone to be able to see that, okay, so this is what I'm seeing. Do you agree with me in terms of, because you're the one who has the domain knowledge and I don't. So I think these are all important factors.
That's great. Well, I think we are running down to the end of the session. So if there are no other questions, we're going to go ahead and close out. But I just want to thank you so much for taking the time to do this today. This was so incredibly interesting. We really appreciate you sharing with us and all of the work that you're doing, because I know that that is certainly leading to us having safer communities. So we appreciate that as well.
Thank you so much. Thanks for having me. And I'll be happy. If there are other questions later on, I'll be happy if you want to send it to me, and I'll be happy to answer.
Absolutely. Well, and thank you to all of the participants who were able to join us today. And for those of you who are on the session, we hope that you will join us next time. For March, we have a really exciting live stream event with the Maryland Safety Service Patrol. So that should be really cool. So again, thanks for being here today. Thanks again to our speaker, Dr. Sartipi, and we look forward to seeing you all next time.
Thank you so much. Bye.